Alright, so today we're going to be working on problem 3.10, which in this problem we have a diver. They're going to jump off into some water here. But they're jumping off this cliff and they need to be able to clear this ledge. So what we want to know is the minimum speed they need to be going in this direction in order to clear this edge and not smack themselves there. So, when we're looking at this problem, there are a couple things we can look at what we know. We know that, well, let's establish a reference frame. I'm going to say that this direction is positive x, this direction is positive y. I think that's a frame that'll be pretty easy to work with. And really, they give this as v naught, but so we don't get confused, why don't we actually call that vx naught? And that's going to make a little more sense because it's not their total velocity. Their velocity vector is actually going to look like that, but it's more of the x component right there. So we know with respect to y, if time starts right here when they're jumping off, our velocity, our initial y velocity is going to be 0. So we know that. And we know that to clear this jump, since we're going to be going the minimum distance, really we'd want to go a little further. If I was jumping, I would. But the minimum distance we're going to say is 1.75 meters. Even though maybe if you just go that far, you might scrape your heel on there or something. And really, we only care about when they clear this ledge. So it's going to be the time when they're pretty much at this point, which will be the time that they're at this height of 9.0 meters. So we know in total we're going to go 9.0 meters in the y direction. Now, we don't know our velocity in the x direction. We know our initial velocity in the y direction. But one thing we do know is we know that in, I'm gonna erase that. We know that in the x direction, our acceleration is 0. Because after we jump off there, she's not going to be going any faster than her initial velocity. And we know that in the y direction, we have gravity acting on us. So we know that the acceleration in the y direction is going to be 9.81 meters per second squared. Now they actually tell us that our diver, they give us her weight, I guess, that it's a 510 Newton diver. Like, that's something important, but really we're not going to use that. That doesn't actually matter. Wonder if they're just doing that to throw us off. So, if we look at that, we can pull up some handy equations to help us solve for the things we want. First of all, we want to know how long is it going to take for her to fall from 0 to 9.0, because that's the amount of time that she needs to go 1.75 meters in the x direction. So what we're going to do is we have this handy equation. We know that our final y position minus our initial, or in other words, delta y, it's the same, is equal to our initial y velocity times time plus 1/2 our acceleration in the y direction times time squared. Now this is an equation that works if we have a constant acceleration, which we do, right there. So all we have to do now is we need to plug things in. So we know y final is going to be 9.0. That's the distance we're traveling, really, so this whole thing's going to come out to be 9.0, this delta y, but I'll write it out anyway, in case you want to solve it this way. She's going to be at this point. That's where we care about. Final. And our initial is 0. That's the origin right here. And then our initial y velocity, well, right here she's at rest before she jumps off. So this term, that's actually 0. So this whole term is actually going to be 0, which makes things easier for us. Because now we just have to worry about this part. Our acceleration, 9.81 t squared. Now this is pretty easy to solve. 9.00, 1/2, 9.81 t squared. We just move everything over to the same side. I'm going to move t over here, but really we're dividing these terms over. 0.00. Sorry for getting a little messy there. Fix that real fast. 9.00 divided by 9.81 right there. Square root both sides. We get t equals square root of 9.00 divided by 9.81. Plug that into your calculator, and it's going to give you 1.36. Now if we look at units, we know that this is time, so it's going to be in seconds. But we can check that. We know this is our acceleration, which is in meters second squared. And this is a distance, which is in meters. So those two are going to cancel out. Second squared is going to be square rooted. We're just left with seconds. So those units look good. So it looks like we're doing that correctly. Now that we have the time, we can use this time to find this initial velocity in the x direction, which is what we want. We're going to use the same equation, but instead of with respect to y, we're going to do it with respect to x. So what we have is our x final minus x initial, and this is going to be the same thing as delta x, equals our initial x velocity times time plus 1/2 our acceleration in the x direction times squared. Now we know this delta x is 1.75. You can do it the same way we did before. You can take the final and initial, or you can just use that delta x because we know that's how far we're going in the x direction. In this case, it's the same because we started in at the origin. It's equal to, we don't know our initial x velocity, but we do know our time, which is 1.36. And one thing we also know is we're not accelerating in the x direction, so this entire term is just 0. So we don't need to worry about that. So now we can divide both sides by 1.36. So you're going to have 1.75 divided by 1.36. And that's going to give you 1.29 meters per second squared. No, per second. I'm sorry. Not squared. It's velocity. We'll check our units here real fast. That's going to be the final answer, but just to make sure we did it right, let's see, this value is in seconds. This value is in meters, it's a distance. So we have our meters divided by seconds, so it looks like our units are right. And here we have our answer.